All right, so we're on page 616, right? Extra practice problems. Right? Page 616, extra practice problems. I know now some of you are taking the content here very seriously. I appreciate hearing about seniors that are going to be doing some tutoring after school. That's awesome. I've encouraged them, with what I told them, we're going to be doing the EPPs here today. Last opportunity to review. Let's go ahead and I'll try to work through all the problems. I did do grading last night. It's obvious that there's some of you all are working the problems, showing your work and getting the right answers. Some of you all are working, obviously demonstrating a lot of work and not getting the right answers. I was considering passing the papers back this morning. I haven't recorded the grades yet. But for those of you that have actually been working the problems, I'm sure you've spent time in those problems, and when we go over them, you'll remember, I didn't get this one. Like a couple of you, I appreciate it when you write on the side question mark or I really don't know how to do this, because it's obvious to me you don't know how to do it when you're doing it, but that helps me know that you know that you don't know how to do it. And there's some of you that turned in just a list of answers. I have no idea if you know how to work the problems or not. You may or may not have gotten the questions right. And for you, you may or may not know if you were doing it right or wrong, and you won't have anything to compare what I do up here today. But hopefully today you leave here with a better sense of, when I see this kind of a problem, here are the steps, here's the thinking that I need to go through to solve this problem correctly. I may present some things in a slightly different way. And one of my fears on these last minute, like day before exams, is that I'll present something in a slightly different way. You believe and you've demonstrated that you already know it, and what I say confuses you rather than helps you. That's just my way to try to appeal to some folks in here that still aren't getting it the way that I've been teaching it. So I may at times, and it's not planned, but I may at times go into another analogy, another way of saying the same old thing. So I want to encourage you, if you have a sense of, I'm in a problem, you already know how to do this, don't let some way I'm trying to explain it to another person distract you from the way you already have figured out that does actually work. Okay? Let's go ahead and walk through the problems. And again, I'll be trying to encourage the thought process of what you need to go through as you see a problem like this. And if time permits, my intention is to open up the exam, which I've only read through once, but I'm going to open up the exam, read through real quickly, and just confirm that we've gone over the ideas today of what you need to know for the exam tomorrow. But there are no new ideas. Everything that's on the exam is something we have covered in class and you have had practice problems on. Yes, sir.
Is this one on the test?
Mm-hmm.
Like, we need to know the symbols for the words. Do we know the words for the symbols?
Mm-hmm. Yes. Just the bold ones, though. So table 2.1, 2.2, and the bold elements from table 2.3. Mm-hmm. So they're no longer going to say chlorine and you write chlorine. They expect chlorine, you're going to write down Cl. In the future, like I said, chlorine is a particular case. It's a homonuclear diatomic. Again, big phrase, may not mean a lot now, but in a few modules, you're going to know that writing down Cl by itself is an exception. Generally, it's Cl2. For right now, if you just know it's chlorine and use Cl, we're good. Let's keep rocking. Okay? So know this. You should, for example, in your mind, you should be able to have a match the symbol with the name kind of mentality. Draw lines, fill blanks. Now, we don't tend to do that juniors and seniors in high school, but think of that kind of an exercise. If I see the symbol, if your flashcards, like I encouraged you last week to make, one side have the name, one side have the symbol, you go through the names, flip it, see if you got the symbol right. Then go through the symbols. Think of the name, flip it. Did you get the name right? You should be able to go back and forth like that for those bold ones. And table 2.1 and 2.2, just know it cold. Just hepa, hexa, tetra, what do they mean? Okay? Yeah, in your book, table 2.3, it's at the end of module 2 before the problems, so you probably need to come this way a little bit. Yeah, right there. On the right-hand side, the ones that are bold. The ones that are in bold. Okay? All right, start from the top. Please, if you have questions today, if you want me to address it here in class, you need to be brave enough to say, I don't get that. Mr. Baker, I need to hear that again, or I didn't understand what you just said. Please repeat it. Because otherwise, I'm going to look for the nonverbal feedback. And if I don't get a, I need help, like I don't get that, if it's either got it or I'm just zoned out, Mr. Baker, keep going, so I'm going to keep moving. Okay. If you need something repeated, either ask me or look to your study partner and go, do you understand that? Because we need to talk about it afterwards. Okay. Make note, I need to go over this. Here we go. Extra practice problem number 1. How can you experimentally determine whether a compound is ionic or covalent? Correct. Well, let me, okay, it is rolling. Let me qualify that just a little bit. Is it a metal or a nonmetal? And I saw that kind of language on the exam or on the problems that you turned in. Remember, you're trying to find out if one of the elements in the compound is a metal. Okay? A compound, an ionic compound, has a metal and a nonmetal that are joined together. At least one nonmetal. Has a metal and at least one nonmetal joined together. So when you're looking at the compound, you're trying to find if one of the elements that is in the compound is a metal. Okay? When you say to find out if the compound is a metal or a nonmetal, it's a combination of both. So your answer is partially correct. What you're hunting for is the metal. Now, where's the metal normally going to be found in the symbol? In the symbol. When you see the chemical formula, where are you normally going to, if it's written appropriately, where is the symbol for the metal going to be? It's going to lead. It's going to be the first element in that compound. So the quick, for time-wise, you look at a compound, look to the very first element, and check, is it a metal or not? Take that symbol, go to your periodic table of elements, and find where does it sit relative to the jagged line. Okay? If it resides to the left-hand side, except for hydrogen, which is the exception, it's a metal. If it's to the right-hand side, or hydrogen, it is a nonmetal. So by looking at the first one, you can tell whether or not the compound is ionic or covalent, because if it's a metal, it's ionic. If it's a nonmetal, it's covalent. Okay, but the first question here, we just answered the second question. The first question was, how do you experimentally determine whether a compound is? Yes, sir?
Metal has electricity.
A metal, okay, again, let me qualify that. You're right. On a multiple choice question, you would have got that right, okay? But on a qualitative answer, as opposed to a quantitative answer, according to the Google answer, you would have gotten it wrong. Here's the deal. Does everybody know what I meant by that?
Yes.
Yesterday when I said, those of you that Googled what the qualitative versus quantitative is, quantitative deals with numbers, qualitative deals with words and explaining things. In chemistry, quantitative means I need exact measurement. Qualitative means give me a ballpark. It's a little bit different. So, when you said it has electricity, here's the deal. When you mix a covalent compound in distilled water, pure H2O, the molecule still stays together. And that molecule is all non-metal. Now, the reason why it doesn't conduct electricity is not because it's a metal or a non-metal. It's because it's covalent and it doesn't break into ions. However, when you put an ionic substance in distilled water and you dissolve it, the ions break up. Now, yes, that compound has a metal in it because that's what made it ionic, but it also has nonmetals in it, and they both become ions, right? And again, this is another concept where you're kind of pushing into a future module. Your answer is a little bit more detailed than it needs to be right now for Module 2. The answer here is because as you mix it up, the metal and nonmetal separate and they create ions which allow electricity to be conducted. So for Module 2, it's just simply, if I mix up an ionic compound, it will conduct electricity. It does that not because it has a metal in it, it's because it's ionic. But it has to have a metal in it in order to be ionic. Okay, so it's a little bit nuanced of an answer there. But because when you dissolve it, it breaks into ions, and the ions then conduct electricity, experimentally you can find out whether it's ionic or not by dissolving it in distilled water and seeing if it conducts electricity. If it conducts electricity, it's ionic. And if it's ionic, it contains a metal. See? So it's not the metal per se that's causing electricity because the nonmetal ion also participates in this electricity transfer. Okay. So the first one, experimentally, dissolve it in distilled water. If it conducts electricity, it is ionic. Second one, from the periodic table, find out if the compound has at least one metal in it, which should be the first element in the chemical symbol of the compound. Find out if that first element is a metal or nonmetal. If it's a metal, it's ionic. If it's a nonmetal, it's covalent. See, the first question, you may not even know what it is. Someone may come up to you and say, hey, Ray, find out if this powder here is ionic or covalent. You go, but I don't know what it is. Don't need to. Dissolve in distilled water. Does it conduct? Yes, it's ionic. Knowing that's ionic, now you know it's a metal, and then you go to future tests of how to figure out exactly what the metals are. But the first step is, does it conduct? Okay. Number 3, which of the following molecules are covalent? So when you get a question that says, look at a molecule, or look at a set of molecules, determine whether it is ionic or covalent, I want you to think this way. It's covalent unless I find a metal. It's covalent unless I find a metal. Now, let me look at the first element. Is it a metal? If you don't find any metal, it's still covalent. If you find a metal, it's ionic, right? So looking at the book on SO2, sulfur and oxygen, it's covalent. Do I find a metal there? No, it's still covalent. The second one, magnesium chloride. I assume it's covalent, but I look at the first element, Mg, magnesium. I come over here, I find Mg on column 2. Is it a metal or a nonmetal? It's a metal. So I was wrong. It's not covalent. It's ionic. Why? I found a metal. Third one, sodium iodide. Again, first element, I'm assuming it's covalent, but the first element is sodium. Sodium is a metal, therefore I was wrong. It's ionic. And the last one, C2H4O. It's a CHO molecule, CHO in different combinations. Carbon, hydrogen, oxygen, those are all nonmetals. And one more time, you don't know that they're nonmetals because they're not solid. Somebody here keeps putting down, I know it's a metal because it's solid. That's not true. That's not a way you qualify a metal. It has nothing to do with its phase, whether it's a solid, liquid, or gas. A metal is a metal because of the way it acts chemically, not because of the form it's in. Mercury is a metal, but most of the time you see mercury in thermometers and it's a liquid, but it's still a metal. Okay? So get the idea of solid means metal out of your head. That's not true. That's not the way these things are determined. So carbon, hydrogen, oxygen, I assume it's covalent. Do I find a metal? No, it's covalent. Number 4, which of the following are ionic? We'll just go the other way. I'm assuming it's covalent unless I find a metal. And where do I find a metal on the 4 options for number 4? Does A have a metal in it? No, so it's covalent. It's not the right answer. Second one, it starts with Rb, rubidium, right? That's a metal. So guess what? B is ionic. The third one, silicon and oxygen? No, it's covalent. Last one, sodium sulfate. Na is a metal. It's ionic. So the answer to number 4 would be B and D are the 2 that are ionic. So again, does it make sense? We're going to attack these kind of problems by looking at the compound, assuming it's covalent, looking at the first element. If it's a metal, it's ionic. Otherwise, we were right the first time. It's covalent. Now, you could do it the other way and assume it's ionic and then not find a metal, but I think that's a little bit confusing. So stick to one paradigm. It's covalent unless I find a metal. And if I should find the metal as the first element. Does that mean I don't then scan through and see if my prof is trying to trick me and I intentionally wrote it in the wrong format? I'll still scan through it, but generally we don't do that. Generally it's going to be, if there's a metal, it's going to be the first one, because that's the appropriate way, the standard way of writing the chemical formulas. Number 5. Any questions on 1 through 4? And on those strategies? Not a hand fixing your hair, right? Okay, just checking. Uh-oh, this could be bad. Okay, Ray. What's the deal here? I have to blame somebody. Can't be my fault. All right, I'll blame Mr. Parker. How can this happen? Number 5, over here. I, being an engineer, I figured out how to do it. Number 5. Problem says, in order to burn a 5.13 kilogram log, oxygen has to be added. If a chemist collects 1.04 kilograms of water and 308 grams of ash and 5.05 kilograms of carbon dioxide, then how many kilograms of oxygen are needed? I wrote the steps down over here between them, but these steps actually are going to be the way we attack most of these problems. There's 4 different kinds of problems, I think. At least 3, but maybe 4 different kinds of problems that you're going to see. But they're all based on the same basic ideas and the same basic process. This one over here, we're going to start with the equation. This is going to be conservation of mass question. Hopefully you saw that. I've got a certain amount of mass. I'd have a certain thing that I don't know the mass of, and then after the reaction, I have all the masses. I'm trying to find that one unknown thing. So the first step is to write a good reaction equation. Right now, we're using words. Like I wrote, log plus oxygen reacts to produce water and ash and carbon dioxide. So having that written down first is the best way to start. Get a good reaction formula down in the best way you can do. Like over here, I used water. I wrote water. I could have written H2O because you all know that. Over here, carbon dioxide, I wrote CO2. Hopefully you can see that and see the CO2 and recognize that as carbon dioxide. Again, that's part of the requirement. So like in the problem where it says 5.05 kilograms of carbon dioxide were collected, they would expect you to be able to write CO2 because carbon dioxide is, this is the symbol for carbon dioxide. So we've got a log plus oxygen produces water, ash, and carbon dioxide. And they gave me the masses of certain things. So what I do is underneath that equation, I write the masses that I was given. And then I just know from conservation of mass, or law of mass conservation, that everything on this side of the arrow, their masses, when combined, must equal the mass of everything in the product side of the reaction. The mass on one side has to equal the mass on the other side. Now, the most common mistake for those of you that actually showed your work on this problem was that you failed to recognize that everything is in kilograms except for this. It's in grams. The units have to be the same. You can't add a gram and a kilogram without recognizing the units. So you need to get them in the same units. What I did here, if you can see the math, is basically I converted everything to kilograms because I have all but one of them in kilograms, and I'm asked to solve the problem in kilograms. So what I'm going to do is go through and convert 308 grams into 0.308 kilograms. And I did that here, this portion of the math. See, it's 1.04 plus 0.308. That 0.308 is 308 grams rewritten as kilograms. So 1.04, 0.308, and 5.05 kilograms, that's the mass of all of my products. They add up to be 6.398 kilograms. However, my least precise answer, since I'm doing addition, the least precise only takes it to the hundredths place, which means I can only be precise to the hundredths place. I look to the right, it's 5 or greater, which means this gets rounded up. That becomes a 10, which we can't write, so this gets rounded up, and 6.40 kilograms is the sum of those 3 masses on the product side of the reaction. The mass of everything on the product side has to equal the mass of everything on the reactant side. And so I've written that as 5.13 kilograms plus X kilograms, and X kilograms is the mass of the oxygen. So I need to balance this. 5.13 kilograms plus X kilograms, the mass of the oxygen, has to equal the 6.4 kilograms, the total mass on the product side. I solve for X by subtracting 5.13 from both sides, and my answer is that X kilograms is 1.27 kilograms. So 5.13 kilograms of log plus 1.27 kilograms of oxygen produce 1.04 kilograms of water, 0.308 kilograms of ash, and 5.05 kilograms of carbon dioxide. Again, most of you that showed the work, you get the principle. If you messed up, it was not converting grams to kilograms. Any questions on number 5? Concept-wise, any questions on number 5? like the idea of conservation of mass. That everything that we start with, the mass of everything we start with, has to equal the mass of everything we end with. Second part, writing it down correctly. Third, getting the same units. Fourth, solving for the unknown. Number 6, and I know we're going to be slower after these two because I'll have to write it down as we go, but let's keep on cruising then. For number 6, let me read the problem and you can look on the board. It says, in making calcium chloride, so I know the product is going to be calcium chloride. It's the product. I'm making this. So I'm starting with something, have a reaction to produce calcium chloride, and that's why calcium, the CaCl2 on the right side of the reaction arrow, was the first thing that I wrote. In making calcium chloride, 100 grams of calcium plus 100 grams of chlorine makes 156.5 grams of product. Again, it said in making calcium chloride, it makes 156.5 grams of product, along with some leftover calcium. Hopefully you can see that from that top equation there. 100.0 grams of calcium plus 100.0 grams of chlorine produces 156.5 grams of calcium chloride and some unknown mass of excess calcium. How much chlorine and calcium should be added together to make 1.500 kilograms of calcium chloride without any leftovers? So in your mind, you're saying, oh, this is a come up with the perfect recipe problem. Come up with a perfect recipe. Oh, and I'm also going to then need to make batches of that perfect recipe. Okay. Now, in chemical terms, that means come up with a balanced reaction equation and then compute the reaction multiple. So the first thing we're going to do is write down the equation. As I read it from the text, hopefully you saw it, and all the different parts, 100 plus 100 produces 156.5 plus an unknown amount. Write down the equation. Find the excess. Look to the question, or look to the reaction equation you just wrote down and say, was anything not used? And how do we know if something was not used in the reaction? It shows up twice. It shows up in both the products and the reactants. If it shows up, if the same exact atom or molecule, when I say atom, I mean on its own. Of course, there's calcium over here and here, but I'm saying in its structure that's on the equation. If it's a calcium atom, not part of a calcium chloride molecule, if the chemical formula shows up, or the chemical symbols show up on both sides, then you had too much of it. In this case, we had calcium and chlorine that were added together, and we've got a new molecule, a new product, and then we've got a repeat. Calcium is here, and calcium is here. I have too much calcium. Why? Because if I didn't have too much calcium, there would be nothing over here. It would be perfectly balanced. If I'd run out of calcium first, then I would have extra chlorine over here. So the next part of this is to go through and find, what do I have too much of? Whatever I have too much of, I actually needed less of it to start with. So if you were to indicate that by going, okay, here's calcium, oh, there's calcium again, okay, I've got too much. Whatever too much I have, I'm going to get rid of it from my initial equation. I'm going to bring this number down so that I don't have anything left over. Now, since I can figure out how much I had left over, and I know how much I started with, I can figure out how much I should have started with. So we find the excess, and how much is that excess? Well, we've indicated that it's the calcium, but I'm going to go through and say, okay, if I use conservation of mass, the sum of the masses of my reactants has to equal the sum of the masses of my products, and I wrote it this way, 100 plus 100 equals 156.5 plus x, x being my excess calcium. I'm going to solve that for x and find that I have 43.5 grams of calcium in excess. Now, you can show this work, but hopefully you could also see that, hey, I started with 200 and I ended up with 156.5. Whatever I needed to make my 200, that's what was excess. That's all we did here mathematically. 156.5 plus what equals 200? And we figure out that 43.5 grams of calcium were in excess. So I had 43.5 grams too much calcium. So let's do the reaction again, but let's not use what we don't need. We don't need 43.5 grams. So I'm going to take my original 100 grams and I'm going to subtract the extra from the calcium. 100 minus 43.5 grams to give me 56.5 grams of calcium. That's all I really needed. Plus 100 grams of chlorine to produce 156.5 grams of calcium chloride. And here you can do conservation of mass again and look at it and say, hey, the sum of the masses of my reactants has to equal the sum of the masses of my products. 100.0 plus 56.5, does that equal 156.5? Yes. Okay, I'm right to this point. I've got it to this point. I've balanced my reaction equation. Or, the way I've been teaching it for Module 2, I've come up with the perfect recipe for this much. The perfect recipe for this much calcium chloride. However, the problem doesn't say produce this much calcium chloride. It tells us it wants another amount. So before you can figure out how much you need in the end, you need to figure out a perfect recipe or a balanced reaction equation that you'll use to get to the end. This would be the recipe for one particular kind of batch that we're aware of. This is true, a true statement. And it produces this much, but that's not how much I've been asked to produce. So I need to figure out how many batches I need to produce. Remember, when I say how many batches, it's not like cupcakes and things where it's going to be a nice even multiple, 2, 3, 4. You know, it'd be like saying, okay, here's your recipe to make a dozen. I want you to go out and make 37.298 cupcakes. It's not going to be a nice even number. It's going to be a fraction. Remember, if you're asked to make an amount that's less than this, your reaction multiple is going to be less than 1. If you're asked to make exactly that amount, you could say, well, my reaction multiple is 1. If you're asked to make more than this, your reaction multiple is going to be more than 1. What is the reaction multiple? Fourth step. How much have I been asked to make? How much do I need to make? Divided by how much I know I can make with whatever recipe, balanced equation I've come up with. This balanced equation here, or this question has asked me to make 1.500 kilograms of calcium chloride. That's what I'm trying to make. I have a recipe that I found in, Grandma's cookbook here. I have a recipe that'll make 156.5 grams of calcium chloride. So I have a recipe for my known that'll make this much. Now notice, they have to be in the same units again. I'm asked to make 1.500 kilograms of product, so my number that I use here has to be in the same units. Remember, reaction multiple technically has no units. So my units have to cancel each other, like that. Which is why the math here, rather than writing down 156.5 grams, I put it in the form 0.1565 kilograms. And I took it out 4 places because I had them, they're significant. And also noticing up here there's 4 places as well, which is why my answer is out to 4 places. So 1.500 kilograms divided by 0.1565 kilograms, hopefully you see that's a little bit less than 1/10, which means my answer here is going to be a little bit less than 10 times. But even if you didn't see that, you just plugged in your calculator, doing the math here would give you 9.597 as my reaction multiple. What does that reaction multiple of 9.597 mean? In order to make this much product, I need 9.597 batches of this recipe. So, just like we would on a recipe, if you were making a 9.597 batches of cupcakes and the recipe called for 2 eggs, you would be adding a little bit more than 19 eggs to that batter to make that many cupcakes. I need 9.597 times the recipe. And the recipe is your balanced equation. So, I take my balanced equation right here, and I rewrite it again, but I multiply every component, both reactants and products. I multiply every mass of everything in that equation by this multiple. So it was originally 56.5 grams of calcium. It's now 56.5 grams times 9.597 grams of calcium. And it was originally 100 grams of chlorine, but now it's 100.0 grams times 9.597 grams of chlorine. To produce, the original product is 156.5 grams of calcium chloride times 9.597 grams of calcium chloride. And when I do the math, my first check to know that I did this reaction multiple correct is that my product times my multiple should equal what I've been asked for. I was asked to produce 1.500 kilograms. Is that what that math turns out to be? And if it does, then go back and do the other math. Multiplying these out, so the answer to question number 6 is 542 grams of calcium reacts with 959.7 grams of chlorine to produce 1.500 kilograms of calcium chloride. So you write down the equation, you find what you have excess of, you balance the equation. After balancing the equation, if it tells you to make an amount other than what the recipe will make, you figure out how many batches you need, and then you multiply every mass by that reaction multiple. You may have noticed on the extra practice problems that this middle section, 5 through 9, are very, very similar. So if you understand this process, it's going to put you in good stead to answer problems like this. I'm trying to remember, one of these problems has a slight twist to it. Why don't you guys help me out? Between problems 6 through 9, let's do this. We'll go 10 through the end, just these 3 problems, and then I'm going to ask you to help me out with 6 through 9, which ones you'd like to go over. If there's one in particular you didn't understand. One of these has a twist in it that I can't see. It's not obvious to me now, but once I work in the problem, it'll pop out. So after we do 10, 11, and 12, then we'll come back and I'll hear from you 6 through 9, which ones you want to do, in what order, and we'll work through the end of class on those. Number 10, let me make some space. I'm actually going to leave that center section on the whiteboard with the process, because if we can see how much we use that again with some of the other problems, and there might be some tweaks we make to it. All right, so we're jumping down to number 10 right now. Give the chemical formula for each of the following compounds. Just as you look across that real quickly, you see in some cases they've got the prefixes on there. Now, if you write the prefix with a hyphen, I actually encourage you to do that at first. Di, tri, tetra. You don't have to put the hyphen in there. You know what I mean by that? Like dioxide. Sometimes I write di hyphen oxide. But if you want to write that for now until you get real comfortable, because sometimes without the hyphen, it kind of all blends together, and you're going, what's a dioxide? Oh, that's a dioxide. Okay. You can put the hyphen in there. You know, there's no issues with points and stuff for that. I'm looking that you recognize the dioxide and what that means. So if you put it in there or don't put it in there, there's no crime, no foul on that stuff. I want to make sure that you can see that that di is appended to, it's added to the chemical name. So whichever way you're comfortable, that'll work for now. Number 10, give the chemical formula for each of the following. Let's look at A. Strategy, what are we going to do? Let's first of all go through and see if we can find the chemical or the elemental names. What are the names of the elements that are in that compound? 10A. What's the first element? Phosphorus, right? So this is a case where, having the table memorized, we can say the first element in this compound is phosphorus. I need to write down the chemical symbol for phosphorus, the element phosphorus. And what is that? Just a P. It's a P. That's phosphorus. Let's not worry about the prefixes yet. Let's just get the names of the elements down. That's phosphorus. What's the second element we find in this name? Oxygen. It's got an oxide. It should be the last element in the whole chemical formula or chemical we're looking at because it ends with an "ide" name. If it wasn't the last, it would be oxygen, not oxide. Okay? But it is the last, so it gets its "ide" name. So the second one is going to be O for oxygen. Now go back to each one of those chemicals. Phosphorus, does it have a prefix? It does. It has a prefix di on it. Di from table 2.1 or 2.2. Can I get them mixed up? Di means how many? 2. Where does that 2 go? Though in the name it's said first, in the symbol it's written after it. So it would have been diphosphorus, but when we write the chemical symbol, we put the di as a subscript after the element. So this is diphosphorus. The second element was oxygen with the prefix hexa. Hexa means 6. Again, it follows the element and is subscripted this way. So diphosphorus hexaoxide is P2O6. And in the other direction, just like we're going to do in number 11, if I were trying to say what is the name of this compound, you would cipher it by saying it's diphosphorus hexaoxygen. Oh, it's the last one, hexaoxide. B. Name of the first element. Nitrogen. Symbol is just an N. Okay. Second element. Hydrogen. Is it the last one? Yeah, it is. So we get an N and an H. So we know the elements involved are nitrogen and hydrogen. What are the subscripts going to be? The subscripts come from their prefixes as written in this form. So it's a dinitrogen. We've said di is 2. So it's 2 nitrogens and hydrogen, tetra. Prefix tetra means 4. Good. So dinitrogen tetrahydride. And C. Name given is nitrogen monoxide. First element is nitrogen. Second element, oxygen. It's an oxide. Looking for prefixes. Do we have one for the nitrogen? No. Technically, what is it, though? It's a mono, but we don't write the mono, right? So this would technically be a 1, but to most accurately, by convention, we never write 1. Because if it wasn't at least 1, it wouldn't be here at all. So just the fact that we wrote down an N means there's one of them. If there's more than one of them, we need to indicate that. And that oxide does get the mono because it's not a leading mono, but that just confirms for us that this is one of them. So again, this is nitrogen monoxide. And every one of these is what kind of a molecule? These are all, they're all covalent, right? Because every one of them had a prefixed name. Every one of them had a mono, di, tri, tetra, something in front of them. And that is the naming paradigm for covalent molecules. If you had something that did not have a prefix in it, you would have to assume that it is ionic. Because at least the second element, even if it was just like this case, is this covalent or ionic? Well, you know what? If this were ionic, it would just be nitrogen oxide, not nitrogen monoxide. See the difference? The fact that I have a monoxide in there tells me it's covalent. Because if it were ionic, there would be no prefixes at all. None in the name. So if I look at any element, I see a mono, di, tri, tetra, all through penta, all the way through. If I see any of those, that molecule has to be covalent if it's named correctly. If it's named correctly. Okay. So any questions on this, going from names to formula. 11 is going from formula to name. In 11, we start with SO2. Now, what is the first thing we're going to do when we see a chemical formula and we need to figure out what the name is? Close. Correct. Let's find out whether or not this compound is covalent or ionic. And we'll do that by figuring out if the lead element is metal or nonmetal. Correct. So the first thing we need to know is which naming paradigm are we going to use? The ionic paradigm or the covalent paradigm? And we do that by finding out whether this is an ionic or covalent molecule, compound. And we do that by looking at the first and figuring out, is this a metal or not? In this case, SO2, is there a metal in it? No. So it is a covalent molecule. It will follow a covalent naming paradigm. So I look at the first element, and the name of that element is what? Sulfur. I'm going to write down sulfur. Since it's covalent, I need to keep track of how many of them are there, right? How many sulfurs are there? One. One is indicated by a prefix of mono. Now, in this case, what I'm going to do is I'm going to write mono up there. This is my technique is to write mono sulfur. And granted, we will lose that later on, but I'd rather write it and then erase it than forget to put it on there. Because sometimes what people will do is if this is a 2, 3, or 4, but because it's the lead, they won't write down the prefix. I would rather write down the prefix now and then check it later to eliminate it than to not be in the habit of writing down a prefix for every element. So in this case, it's monosulfur. What about the next element? It's oxygen. Is it the last element? Yes. So it gets its ide name from table 2.1. It's going to be oxygen with its ide name, which is oxide. I'm going to leave room here for a prefix. So it's oxide. Are there more than one? Or, yeah, we know there's a, but we're going to put a prefix on it no matter what it is, even if there is only one. So what is the prefix for this element of oxygen? Di, because it has 2. It has 2, so it gets the prefix di. So right now, my construct is monosulfur dioxide. Then the last thing to do is say, I never record a leading mono. And by leading mono, remember, it's leading the molecule. It's this mono out here. Any monos that are in the middle, stay. The only mono you eliminate is if the mono is in front of the first element. Okay? So if it's di, tri, whatever, it stays. And no matter what it is in the middle, it stays. The only thing you eliminate is a leading mono. So this is sulfur dioxide. The second one. CaCl2. This is the only one we're going to do because C and D follow the same thing. It's the same thing, just repeated. But let's do at least one of each. Now that I've said one of each, first thing we do, look at this and determine whether or not this molecule is ionic or covalent. We do that by looking at the first element and deciding, is it or is it not a metal? Calcium. Is it a metal? It is a metal, so the naming paradigm is ionic. Okay. Because now I've determined it's ionic, I don't need to worry about prefixes. Monos, dis, tris. I don't care about that anymore. My name is not going to include any of that. The only thing my name is going to include is the names of the elements with the last element given its ide name. So let's just look at the elements and write them down in order. The first element, Ca, calcium. You've got that memorized, so that's calcium. Cl, it's the last one, so it gets its ide name. So chlorine becomes chloride. Calcium chloride, and that's it. Because remember, it's ionic, and you'll learn future modules that this molecule can only form in this way. There is no such thing as a Ca2Cl, Ca2Cl2, CaCl3. If you've got calcium and chlorine, if they react to form a molecule, it's going to be CaCl2 every time. Which is why this name can be so much simpler. So think of it this way. I'm going to give it the covalent name. Think of the covalent naming paradigm as the way all of them could be, because if you had calcium dichloride up here, it would be more information, but it would always be calcium dichloride. It would never be calcium trichloride or something else. So think of it this way. Assume you're going to use the full naming paradigm with dis, tris, prefixes, but then say, oh, wait a minute, it's ionic. I get a shortcut. I don't have to do all that work. I just need to know the element names and write them down in order as they appear. Calcium dichloride. No, wait a minute, this is ionic. I get to do the easy one, calcium chloride. So ionics, no prefixes. Covalents, every prefix except the leading mono. Question 12, talking about elements, compounds, heterogeneous and homogeneous mixtures. Way I would hope you would approach these kind of problems is like this. Okay. First of all, is what I'm considering an element? Meaning, does it have a symbol on the periodic table? Can I go to this chart and find it? If I can, it's an element. Or can I find what I'm considering? Can I construct it using elements from the periodic table and have every molecule in my sample be exactly that same molecule? See, if I have a sample in my hand and everything, for example, we talk about copper wire. If everything in my hand is copper, if everything in my hand is Cu is copper, okay? So if everything in my hand is an atom of the element copper, my answer is it's an element. It's a pure substance, which I call an element. So in this case, C is an element. Or B says that I have a bottle of H2SO4. They've given me a chemical symbol, and they've said that every molecule in that sample is that exact same molecule. Well, it's not an element because it has multiple elements in it, right? It's a compound, but it's still a pure substance. So it's a pure substance that is a compound. The two mixtures we have to consider are A and D. A bowl of milk and cereal. And remember, when you're looking at mixtures, you're trying to determine, is it heterogeneous or is it homogeneous? Is it heterogeneous? Does it have different pieces and parts? Or is it homogeneous? Is it the same all the way through? And so in these two examples, you've got cereal, a bowl of cereal, and hopefully you can recognize that there'll be places in your bowl of cereal where there's just milk and places where there's just cereal. It's not the same everywhere. So it has to be a heterogeneous mixture. And then the Kool-Aid side, assuming you haven't hypersaturated it, you put the Kool-Aid in and you mix it up, and you take different samples at different places, and you know what? It's going to be virtually, I'll use the word virtually, identical everywhere you go. Because the sugar in there is going to evenly distribute out. It's not like the top is going to be sweeter than the bottom if it's mixed, right? There's no fundamental differences. There's no layers in it. It doesn't separate out. So in that case, Kool-Aid would be a homogeneous mixture because it's the same throughout. Cereal would be a heterogeneous mixture because different places have different characteristics in your bowl of cereal. Some of it's solid, some of it's milk, some of it's your little Lucky Charms. They're all there together. Kind of like a cookie. A cookie is a mixture because you can't find the element cookie and you can't define the compound of cookie. So it has to be a mixture. And if it has different places, like if you have chocolate chip cookie, sometimes you could have just pure chocolate, and sometimes you have just cookie, and sometimes you have chocolate and cookie, and sometimes, you know, or maybe think about your own nature, your own selfishness. Are there times when I want more chocolate, and so I give William the cookie that has only one chip, and I take the one that has 17 chips? Sure. Why? Because I'm greedy, first. Second, because it's a heterogeneous mixture. Not every cookie is exactly the same, and not every place on every cookie is exactly the same within the cookie. So it's heterogeneous. It's different in different places. Okay, We are very short on time. If we were to do one more problem, is there one in particular that you'd like to review? Number 8 has been asked. Anyone else have another opinion between 6 through 9? We'll tack 8. We'll do what we can. I'll dismiss you as soon as I can after a thought at the bell, and we'll just go from there. All right, so number 8. Number 8 says that if you react 12 grams of carbon with 4 grams of hydrogen, you will make methane with no leftovers. I'm sorry, I just happen to know what that is. So don't worry, you could have written out methane. But no leftovers, which means, what does that mean? If there are no leftovers, there are no leftovers. This is a perfect reaction equation. It's already balanced. So whatever that is, since that, we can look at conservation of mass and how much methane do we actually make? 12 and 4 is 16, right? And I'm only going to go precise out to the tenths place. 16 grams of methane. If a chemist reacts 150 grams of carbon, this was the one I was looking for, thank you, with 150 grams of hydrogen, how many grams of which element will be left over after the methane is made? Okay. Do you see that in the original reaction equation, I know that it takes more carbon by mass than hydrogen to make methane? So if I give you equal amounts, which one is going to run out? The one that takes the most, right? If it takes 12 grams to make 16 grams, however many I put together, if I give you equal amounts, 150 grams and 150 grams, since for every batch this one takes 12 and this one makes 4, however many batches I'm going to make, this is going to run out first. It's like saying, okay, you have, this recipe takes 3 eggs. Well, we don't have time to get complicated, but here's the idea. How many batches, what's going to run out first? Like carbon's going to run out first. What am I going to have extra of? I'm going to end up with extra hydrogen. Now the question is, how many batches can I make? And you come up with the reaction multiple by taking this over this. You divide 150 by 12 to figure out how many batches you could make. Okay? And then work the math backwards to figure out how much hydrogen would be left.